Hi everyone. Today I'm gonna show you how to set up the pipe flow. So this is the first part where I talk about creating a polyhedral mesh, and this is a workbench window, and this starts with the geometry, this space claim, and here in this space claim, choose appropriate view, and then start with creating a rectangle uh, of size, the radius of the pipe that we want and the length of the pipe that we want to investigate. So here I'm looking for 1-inch diameter pipe, so I'm going to go for something like 12.7 mm and 2000 mm, that's 2 meter. So once I create this, I can just have to pull it up using the revolve and taking x-axis as the axis of the pipe, and you can go for entire pipe or you can go for 30-degree sector to save computational time. So here you can go any angle because it's a periodic nature of the pipe. So assuming the flow is periodic, and we just need to simulate for 30-degree sector, and this is a simple pipe flow without any body force, so we can easily assume the flow is periodic, rotational periodic to be precise. So once you are done with the geometry, you can start naming the important phases such as inlet and then the periodic phases. Okay, we can give any periodic 1, A or whatever, so that we can remember, and periodic 2, and same thing for the remaining one is outlet and the wall. So after this, we can see that it's just a 30-degree sector with a full length of pipe. You save this geometry with some appropriate name, and so workbench will have in the directory, but I recommend you to save it for your reference in some known location. Uh, so this is pipe sector geometry, and we're done here. I don't need this one. I can directly go with fluent meshing. In the fluent mesher, you start with double procession, and in the serial mode, you can only mesh 3D geometry in the fluent mesher. This is an ANSYS R19. Okay, so start with import CAD geometry, and the import, choose appropriate unit. If you are working with mm, choose mm. If you are working with inches, you put inches. Leave everything else same, do not modify. You can do refined faceting if your geometry, if you need to capture some highly curved or highly narrow region. Otherwise, normally you don't need to do anything here. So this will take some time to load. Couple of minutes, and yeah, so here we loaded. You can see in the console. Okay, this is my console, and in the console window you can see the summary of the geometry loading, and you can see the names that we tagged are shown in reflecting in the fluent, and you can visualize this geometry here. If you are working with complex geometry, it's not advisable to draw every faces at the same time. uh, okay, so here in this first part we'll tell Fluent about the rotational periodicity. We have to set this periodic phases, and so you can go to the model and go to periodicity, and here you can give the degrees of the sector, and then you have to give the proper pivot point, which is origin in our case, and the axis of rotation, which is x-axis. So once we define this, you can see the how you understand this, and this is what we want. So we'll go forward with this, and now we can define our sizes, mesh size. Generally, Fluent will calculate the mean and max for you. You can go with that as of and you can modify if you want more control over the mean and max. Then you can start with the sizing. So first let's give some name like curvature, and the type is curvature face sizing. Normal angle will govern the amount of division on the curved faces. You can select any face or edges. Here I'm going with all the face and edges, like a general curvature sizing, and yes, and a create curvature size. Next, go for proximity. I You can go for cells per gap, like default is 3. You can increase it to create more cells in the gaps, and I override the curvature. Let me correct this one again to curvature. Yeah, sorry. Okay, so to create new sizing, you have to just click on the white area again, and then just go to the name and give some name like proximity or any name you want, and change the type as proximity here, and give proper cells per gap, uh, and then again create. So these are general curvature and proximity sizing we provided for our geometry. Now we'll go for very specific sizing, like we want to refine our wall with soft sizing. Let's see if without specific sizing, what are our cell size. So you can see these 3 boxes, and you can assume that these are the sizes that it will generate, and these are pretty big. So what we'll do, we can modify this curvature and proximity to refine them more, or we can give the wall as a specific sizing, because that's where we need more refinement to capture appropriate flow in the boundary layer. And here you can immediately have an idea of the length scale, like this. Approximately it's around 6.38 mm. So now we go for soft specific sizing. So here we go for wall. We want to give a proper like specify the cell size here, and we go and just select the wall as a phase zone label and create. So you can give the max as 1. So Fluent will make sure that cell size is greater than or less than or equal to 1. And when you calculate it, you see that it has slightly reduced, and you see how the cell size grows from the wall to the axis. So it's still very coarse mesh. We want to refine it further. So let's modify it to something like since we have long length, we cannot refine it too much, otherwise we have large cell size, large cell count. So we'll do it half and see. And once the cell size is completed, we just check again. Oops. Yeah. So you see it's now it's still coarse, but we can work with this just for the demonstration purpose. And then we can export this as size field. This is the information that Fluent Mesher needs in the second round to create surface mesh. So we'll save this size field as some name like size1 dot size, and that's it. The size field is, we have the size field, and you can import in the same session, but let's keep this session separate so that we can come here and modify again if you want. Open another session. So you can create a separate session in the workbench itself, or you can create in a different like a standalone Fluent session. The workbench here I'm showing this for your reference to show the schematics of the process. Like you go from space claim, and then from space claim you put Fluent mesh here. Yeah. So again we import CAD, and this time we change the tessellations to CFD surface mesh, and we use the size field what we just saved, size1, and you have to be careful with the units. Make sure it's the same unit that you have created the size field. This will take slightly longer time than the CAD import. Okay, I think it's done. Okay, so once it shows done, you can go here in the mesh object and you can draw all if your mesh is simple. Let's do for the wall and just see the how did we discretize the wall, and you can see that we have a good mesh on the wall. It's still like not very defined, but we will just go with this and see the periodic. How the mesh grows from wall to the axis. So now we go to summary and we check the number of faces. If it's too large, then definitely something is wrong. Uh, you have to, or if it's too small, then it's gonna give a very coarse mesh. And you have to go to recover periodicity in the mesh object, and you'll see the rotational periodicity already applied, and you have to just select the face periodic 1 or periodic 2, and I select 2, which is by mistake, but I actually have to select only 1. And you see the number of cell count on the both faces are different right now. And when we do recover periodicity, so it recover for periodic, like in the process like you just have to select one of them, but I mistakenly select 2. Okay, now if you see and try again on the single one, it will give some error. So once it is done, it won't. So this shows like they are in periodic pair, and when you list them, the cell count is exactly same. So this is like a one face is a shadow of another face, and like they are conformal in nature. So you can see from visually that the faces are one-on-one mapped on each other. So now the next part is to compute the volume, and we can have a change the name to fluid. By default it is solid, and then go to auto mesh, select the object. If you want boundary layer mesh, then you can go here and select the appropriate method you want, and you can decrease or increase the number of layers. And I just keep the default value, and you need to show what you can name them, like select by name, similar like any other measure. And I go with the face labels, and in the boundary I select only wall. Great. So this will control the modular mesh, and you can change the method if you want. Let's go with the default, and before doing, we can confirm with by what are the faces that the prism will go. And that's it, we are ready for polyhedral. And here you have to select size fill, very important step, and then merge cell zone within region, apply and mesh. And then you can monitor uh, the, the log, and you can see how prisms are created. And so all the layers are layer by layer will create and will summarize. So here I have to check the quality of the prism, and you see there is no stair stepping as of now. Yeah, there's no stair stepping. The prisms are smooth. It has created 200,000 cells for just for boundary layer, and then now we are going for, initially it will create tetrahedral mesh, and then it will create a polyhedral on that. So if you are going for a large mesh, it will take significant time, but uh, so we are done here for this mesh. So it's like with together with prism and total uh, core mesh, we have around 500,000 cells. And you can go here in the cell zone, and you can go for summary, and you can check the skewness. This is very good, 0.42. Anything less than 0.9 is good. And further, all other aspect ratio can be checked in the report. So the next step is to prepare for solve, and before you go to solver, and this will remove the unused nodes. And now the mesh is ready to go for the solver. So we write it as a mesh file, give some volume mesh name, and we're done. So once we write it, we can, after saving the mesh, we can draw the boundaries. So we can see how the tetrahedral mesh it looks like a poly now, and you can see the prism, and they look pretty good. Coarse, of course, but we can refine it by more soft sizing or cells per gap in the proximity. And now let's see the internal mesh. We can create appropriate clipping plane, and on the clipping plane we can draw the cell layer, and Fluent will display cells, the internal core structure of. So this looks like this is how polyhedral mesh looks. Prisms look like bricks, and so this is my first video, and in the second part we'll study about how to set up this case further. Thank you.